Hi, Bello. How are you?
Steady like a leaf.
Yeah, you look nervous.
Really nervous.
Yeah, really nervous. Okay, tell me what you're going to be doing.
Last time I got yeses from everyone except from you, and I told you I will do anything to impress you.
And hang on a minute, I'm not taking responsibility. I didn't ask you to do this.
Kind of did.
You did kind of do that.
No, I didn't. Okay, just tell me what's going to happen here.
Well, hopefully I make it from the cannon over the helicopter and land on the bullseye.
Okay, that blade's going to be rotating?
Blades will be spinning.
Has anyone ever done this before?
This has never been done before. 48 people in history have tried human cannonballing. Half of them have been successful.
And the other half?
Well, the other half died.
Oh my gosh.
Even the ones that did make it have had some major injuries.
What the hell's he thinking? He's lost his mind.
That's my daughter right there. She is watching.
Okay, I think we should just get on with it because I'm feeling anxious.
Good luck.
Wow.
Okay, thank you.
Rooting for you.
Are you all ready?
He is nuts.
Yeah.
We have an ambulance waiting here just in case something doesn't go as planned.
Bello! Good luck, Bello! Oh gosh, Bello.
That'll take off ahead in a second.
Simon, I feel a little sick. I don't like this. Oh my gosh.
Now he's in.
Power cannon. Full power.
Oh my god.
Power.
Army cannon.
Oh my god, no.
Full safety.
Oh.
5, 4, 3, 2, 1.
Oh my god.
I think he's okay though.
You okay?
Is he okay?
Hi, Bello. How are you?
Steady like a leaf.
Yeah, you look nervous.
Really nervous.
Yeah, really nervous.
Go as planned.
So what are the chances that he was not going to be able to make it?
Ahead.
He made it sound like it was like 50-50. Almost like 50% of the people who tried this didn't make it. And it's creating the impression that what he's doing is actually a skill.
Simon, I feel a little sick. I don't like
The reality of it is there's almost a zero chance that something was going to go wrong. It's more of an illusion of danger. How do I know that? Why not? It's the same as this. It looks like something is going wrong. And there is something going wrong here. All right, so this is a failed attempt. It's projectile motion. This one is a failed attempt. How is it a failed attempt? They were supposed to be landing on top of these cars. Why, you may ask? The reason is because the cars will absorb the impact, which means that the cars are there to increase the impact time. So what happens when you increase the impact time? Impact time goes up, acceleration goes down. So that's what happens. And obviously the car is falling short. So the question is why? The car is not supposed to be falling short because this motion should be 100% predictable. And in this instant, it doesn't appear so. So we have to investigate that. All right, so this was one of the main observations of the lecture. He's holding a bullet, she's holding a rifle, same height. As soon as she pulls the trigger, he's going to drop the bullet, right? So the question is, which bullet is going to drop first? All right, common sense will dictate that this is going to end up landing first. Some people will argue that both bullets will end up on the ground at the same time. As soon as you make that argument against someone who has no background in physics, more than likely you're going to end up having a black eye because somebody's going to punch you in the face. All right, a lot of people will argue that this is going to land first because of the simple reason that this bullet is falling unimpeded. This one has a tremendous amount of force behind it. In fact, if you were to stand in front of this rifle, it can potentially kill you, right? So this bullet, unimpeded, is probably going to travel half a mile to a mile before dropping. So this is going to be about a mile away, and this is right here. So which one is going to land first? It's a no-brainer, right? So a lot of people will say this one is going to land first. Physics says both will land at the same time. All right, so ignoring the effects of air friction, it's free fall. All right, so as soon as the bullet is fired, released, gravity takes over. So the motion is under the influence of gravity. And what is gravity? Under the influence of gravity, everything is going to fall at the same rate. Everything is going to fall at the same rate. All right, so meaning that everything is going to accelerate at the same rate. So this bullet and that bullet will end up reaching the ground at the same time. So objects fall at the same rate. Objects fall at the same rate, regardless of their weights, regardless of their sizes, regardless of their motion. It doesn't matter if the object is moving the horizontal direction or if it's not moving at all. Everything is still going to fall at the same rate. So that's what it means.
Needed to match the solenoid. Down the room.
Wait to see the high speed. Man, I can't wait to see the high speed.
In 3, 2, 1.
But from 360 feet away, the boys can't see exactly where the fired bullet landed.
Let's go see where it hit.
So Adam takes a one-wheeled ride down the room to check out the drop zone.
Wow.
And the results are simply ripping.
Can't get much closer than that. I can't wait to see the high speed. So, dude, this bullet carved a streak right under the drop zone. I think this might be the shot we've been looking for.
In real time, it's impossible to tell what happened until Adam analyzes the high speed and crunches the numbers.
3677 minus 3915 equals 238 divided by 6. Dude, the difference is 39.6 milliseconds.
Which means it's less than the heat I can make out.
So after days of brain-teasing tests, the Mythbusters can claim a world first for themselves. And a victory for physics.
This bullet.
All right, so in high speed, both of them land at the same time. At least that's the way it looks like, right? So here's the fire bullet. This one is the drop bullet. They end up landing at the same time. And slow motion, though, fired bullet is delayed by 400th of a second. So what does that mean? Does this mean that the physics is wrong? Hardly, guys. It just tells you that there's no such thing as a perfect experiment in real life. All right, so real life is not a Disney movie. Things go wrong. The difference time lag is about 400th of a second. It's called an experimental error. The experimental error experimental error that happens here is less than 1%. It's less than a fraction of a 1% in essence, which means that it's less than a perfect experiment. These guys spent hours setting up this experiment. They repeated this experiment time and time again, eliminating every single mistake imaginable. At the end, you cannot eliminate everything with 100% accuracy. All right, so what happened was, if you think of the amount of time spent inside the barrel, all right, so that explains part of it. And then if you think of the fact that this bullet was spinning just like a football, meaning that it was actually experiencing a little bit of a lift because of the air friction, then you can explain all of it. So it's an experimental error. So both of them end up at the same time for all practical purposes. So what do we know? Which, in the absence of air friction, everything still falls at the same rate. Everything still falls at the same rate. So projectile motion is an example of free fall. This is free fall. This is projectile motion. Notice that the objects are falling at the same rate along the vertical direction, along the direction of the pull of gravity. All right, so here's the ball in projectile motion. And then we can look at the projection of the motion along the horizontal direction as well as the vertical direction. Along the horizontal direction, notice that the spacing between the projections are the same, which means that it's moving at a constant speed. Along the vertical direction, it's speeding up because of gravity. That's what it means.
Process.
All right, so projectile motion is the same as free fall, meaning that everything is going to fall at the same rate. Everything is going to fall at the same rate.
One-handed super receiver, a great style as his right hand comes behind his back. And here, a new trick for Flowers. Not necessarily new in the sport, but there, good kind of the Western civilization. The trick's name is the stripper. We're getting a little crazy here, folks. And also, the rock-solid look at this, over 80 feet. He is traveling with no hands or feet on the bike. Process.
Everything falls at the same rate, meaning that everything is falling or accelerating at the same rate. That's the meaning of the fall at this point. While things are moving horizontally at the same speed, what that means is this person and the motorcycle are falling at the same rate. So, and he's also moving with the motorcycle horizontally at the same speed. And he's able to maintain a constant relative position while feeling weightless relative to the motorcycle. All right, so let's move forward. Full projectile motion. It's the parabola. Projectile motion is going to start up with an initial speed. So VO represents that initial velocity or speed. Velocity is coming in an angle. Initial speed is coming in an angle. So it's going to have two components. It's going to have a component on the x direction. And it's going to have a component on the y direction. All right, so it's going to have a projection on the x and the y direction. It's like if you shine a light onto this arrow, it's going to look like it's got a shadow along the x as well as the y directions. These are known as the components. All right, so 1 second later, it's going to be here. 2 seconds, 3 seconds, 4, 5, and 6 seconds. So this is a 6 second arc. This is a 6 second arc. All right, so let's follow the vertical component of this motion. Notice that it's getting smaller as you're going up against gravity, so you will slow down. As you're going with gravity, you will speed up. That's what it means. If the vertical component of the initial speed is 30 meters per second, that's almost like 70 miles per hour. All right, so 1 second later, it's going to be 20. It's going to be 10 the following second, 0 the following second, 10 again in the downward direction, 20 in the downward direction, and 30 in the downward direction. So notice that the vertical component is going to get smaller going up against gravity at a rate of 10 meters per second each and every single second. And then it's going to get larger at a rate of 10 meters per second each and every single second when you're coming back down. Right, so going up against gravity, it will slow down. Going with gravity, it will speed up. Horizontal component does not change. There's absolutely no reason for it to change if you ignore the effects of air friction. If it's horizontally, say about 50 miles per hour, it's still going to be 50, it's still going to be 50, it's still going to be 50, it's going to be 50 all the way down here. All right, so horizontal speed is not going to change. So that's your projectile.
Charlotte, North Carolina.
All right, so along the vertical direction, acceleration is roughly about 10 due to gravity. It's getting constant. So vertical motion is predictable. Horizontally, the acceleration is going to be 0 because you go from 50 miles per hour to 50 miles per hour. So it's going to be 0. So there's no change in speed horizontally. So horizontal acceleration is going to be 0. It's going to be constant. So which means that the motion along the x direction is also predictable. All right, so what makes motion predictable is the constancy of acceleration. So acceleration is going to be constant along the x direction. It's going to be constant along the y direction. So which means that the entire projectile motion is going to be a uniform motion. It's a predictable motion. So the only thing you need to know, if you set the angle to a proper degree, and if you have the proper speed, you will complete this jump 100% of the time. All right, so if you got the proper angle and you've got the proper speed, the ball is always going to land at this point. The ball is always going to land at that point. All right, so that's the meaning of it.
Carolina. 175,000 racing fans are on hand to watch stuntman Brian Carson attempt a record-setting jump. To succeed, he has to hit this ramp at over 100 miles per hour and leap over 4 flatbed trucks, each packed with explosives that are rigged to erupt in a wall of fire. Then he must land precisely on the red X atop these shock-absorbing stunt cars. In all, the distance he must travel is 250 feet. Brian is ready. A camera mounted inside his car captures a dramatic angle just as he punches the gas on his final approach. But there's big trouble. Brian's jump is well short of the mark, leaving him trapped inside the mangled wreckage.
As soon as the car left the ramp, I knew I was in trouble. I knew it. I feel something was wrong. The car angled the wrong way. I knew the suspension broke somewhere.
Brian's car plunges through the gigantic wall of bursting flames. But instead of hitting the landing mark, he nosedives directly into an explosive charge.
I landed face first, engine first, right in this pyro mortar that was blasting off 100 pounds of explosives right in my face. That's like throwing a dart 100 feet into it and hitting a dime. You couldn't do it.
The force of the explosion and the crushing impact leave Brian fighting for his life. It takes emergency crews 40 minutes to pry him free.
I was pinned, my foot was pinned, part of the car caved in on me, my left arm was shattered, broken. I was in a fog. It was a bad scene.
So what's going wrong here? If that's the case, why is that he's falling short if it's 100% predictable? All right, so that becomes the investigation. So let's just
Charlotte, North Carolina. Mark. Just as he punches.
He's got his own explanations. Of course, his explanations are just explanations, and based on a lot of assumptions which are not correct. All right, so he's making a lot of assumptions. All right, so why is that he's not reaching the target? The reason why he's not able to reach the target is because the car angles the wrong way. All right, so the car angles the wrong way. And because the car angles the wrong way, now the air friction is a factor, right? Air friction becomes a factor because of it. All right, so along the x direction, the acceleration is no longer 0. He's slowing down quite a bit. As a result, he's falling short of the target. Target is located right here. This guy is falling short significantly under the circumstances. All right, so which means that the motion is no longer predictable. Along the y direction, the vertical direction, the motion is under the influence of gravity, and which means that that aspect of motion is still predictable. Along the x direction, the car ends up angling the wrong way, so it ends up slowing down. So the motion is no longer predictable. So the question is, why did the car angle the wrong way? All right, so he did something that he wasn't supposed to, and I know what he did because I could see it in the motion of the car. All right, so when you're airborne, you're not supposed to lock up the brakes. And because the guy's not a physicist, he doesn't know any better, he's thinking, why not? What's the big deal, right? Because he's not on the ground. If you're not locking up the brakes, if you're locking up the brakes, what is it going to do? As far as you're concerned, it's not going to do anything. But what's going to happen is the tires are rotating, the wheels are already rotating. If you lock up the brakes, that rotational motion is going to get transferred to the car. So the car starts to move, rotate slowly in the direction of the rotational motion of the tires when you lock them up. As a result, the car falls short. All right, so he survives because the crumple zone is the portion of the car that takes the initial impact, the second impact, the back of the car, the third impact, the front, the fourth impact, once again, the back of the car. So each impact is a large enough impact on. So that made it survivable. On top of that, he had a few broken bones. So every time you break a bone, that's increased the impact on.
Recording.
Paul Smith, an 18-year-old high school dropout, on the roof of a Florida condominium. Three of his friends have already jumped into the pool below. Paul, unfortunately, misses.
Go, recording.
Paul Smith.
All right, so sideways.
An 18-year-old high school.
All right, once again, this is predictable motion, 100% predictable motion. The only thing you have to do is run and jump. All right, so the pool is down here. It's probably located about 10 yards away from the building. The only thing you have to do is just get up to speed, like 4 or 5 miles per hour, and jump. Okay, you have to do your running before you jump, not after. All right, this guy must have been watching a lot of Roadrunner cartoons because he walks up slowly and then he jumps, realizes that he doesn't have the proper speed, and now he's trying to speed up. It's not going to help you under the circumstances. So he ends up breaking his foot in essence. You will maintain that horizontal speed, initial horizontal speed. It's 100% predictable.
Okay. Daniel, right now it's definitely too gusty. We wouldn't be going for it. It's worse than it was 15 minutes ago.
Get down to 45 miles an hour.
Don't Bob, don't amp down yet.
Stay on over there, we'll get a miracle, which has happened before, and they all come together, but amp down.
Don't amp down.
All right. Don't Bob, don't amp down if you get a miracle.
There's a right way to do it, and there's a wrong way to do it. Absolutely. Yeah. You can't hurry up in the last 2 seconds and haul ass and die 200 feet on fire.
We're playing it to the last minute. It might happen.
Go ahead with the glass.
Go with the glass. Make sure
Our ground air is up to date.
2 to 3 minutes away.
John has just given the okay to wet him. That means that fuel strips soaked in a cocktail are being applied to Bob's suit right now. There's no turning back.
How are we looking up there, Dale? Hey, one more strip to put on him.
Okay, we're 100% down here, guys. We're 100%. We're going. Here we go. Hit the cameras up.
Remember, we're about to see 3 stunts in one. Bob is set on fire and has to wait 8 long seconds for those flames to build before he can finally leap out of that window and free fall 20 stories into this airbag.
Light him, Dane. Light him. Light him. Here he comes.
Okay, come on, right side, take him out. Get in there, boys.
Seeing your incredible free fall in the blur of real time. Now we'll show it to you in what we call movie time. Once again, Bob's perilous leap from 20 stories as captured by 11 film cameras.
All right, so he did this live on TV doing a stuntman commission. The motion itself is so predictable. I mean, it's given a speed and then it's given, and then it was told when to jump in essence. All right, so because the motion is so predictable, they decided to set him on fire first. And then he fell roughly about 200 feet, I think. All right, so a couple of things that he does that we need to focus on. All right, so the motion itself is predictable, but it still requires a great deal of skill to execute something like this. All right, so motion is under the influence of gravity. He's got a constant horizontal speed. The first thing he does, he gets his body upside down. Why does he do that? The reason he does that is because he's on fire. He's trying to protect his eyes. All right, so he's trying to keep the flames away from his eyes so he can see where he's going. And then just before impact, he's going to get his body parallel to the ground. That's crucial. He doesn't do one of those movie landings. A superhero with an American flag ends up jumping and then lands on his one knee and one foot. Right, that's not the way to land. You can break your back doing it that way. All right, so he lands on his back in order to increase the impact time further. That makes it much more survivable. All right, so predictable motion, beautifully executed. So projectile motion is predictable motion.
Now he's
and then you got this 25,000 feet drop
practicing
without a parachute.
That's how he'll have to land. He'll have to land on his back. At 18,000 feet, the oxygen mask will come off. That will be from his cousin, Andy Farrington, who will be closest to him. There goes the oxygen mask. Now at 12,000 feet, you'll hear a beep in his helmet. That will tell him he's halfway home. Momentarily, we'll see his dump team pull their chutes, and that means Luke is all alone for the rest of the way. At 6,000 feet, he'll get another beep in his helmet. There goes the chutes. Luke is on his own. And the crowd on the ground looking up, they have a visual on him right now. He's in.
All right, so he was able to execute this because of the reason that the projectile motion is predictable. But here, the air friction doesn't matter. So it was fairly complicated. That the whole affair was really complicated. He was able to pull it off, though.
Hi, Bello. How are you?
Steady like a leaf.
Yeah, you look nervous.
All right, so this is 100% predictable.
Really nervous. Yeah, really nervous. Okay, tell me what you're going to be doing.
All right, so this was 100% predictable. The only thing that they had to do was figure out the landing zone, and then figure out the speed with which it was supposed to be shot out of the cannon, and then on top of that, get the right angle. So 100% of the time, he was going to hit the target, and of course, he hit the target while creating the impression that this was dangerous.
He is nuts. Yeah.
Beautiful execution. Focus on some other stuff. So both bullets will land at the same time, obviously. All right, so this was a lead-in observation. The main observation of the lecture was the monkey, right? So you got an escaped monkey. You find the monkey. He's hanging from one of the branches of a tree. And you will try to take down the monkey using a cannonball. So cannonball is not going to go so fast that you will kill the monkey. It's just going to go fast enough to stun the monkey. The problem is, as soon as you pull the trigger, it's going to make a loud sound, booming sound. So the monkey's going to get scared. And the monkey's going to release his grip. So knowing that the monkey's going to release his grip as soon as you pull the trigger, where would you aim? You got three options: above, at, and down below the monkey. A lot of people think that you should aim down below the monkey, but the question is how far down below. Okay, so I mean, are you thinking that you should be aiming right at the balls so you can hit them right in the eyes? So we have to come up with a better explanation than that. So we know that everything's going to fall at the same rate under the influence of gravity. And so if that statement is true, regardless of weights, shapes, the horizontal motion as well. So the projectile motion is the same as free fall. So both objects will fall at the same rate, right? Both objects will fall at the same rate. All right, so mathematics is not that important here, so let's go forward. So the only thing you need to know is that horizontal speed is going to be constant, so there's no acceleration on the horizontal direction. On the vertical direction, it's going to be the same as free fall, so g is the acceleration due to gravity. So 0 horizontal acceleration and constant vertical acceleration makes motion 100% predictable. All right, so the angle that's going to maximize the range is going to be 45 degrees. All right, so speaking of the monkey, if you're aiming directly at the monkey, and if the monkey releases his grip at the moment you fire the cannonball, monkey and the cannonball, they're both are going to fall at the same rate from the line of sight. All right, so provided that you have the proper range, 100% of the time you should be able to hit the monkey. 100% of the time you should be able to hit the monkey. So fire the cannonball, the monkey releases his grip. If the cannonball goes fast, you will hit the monkey sooner. If it goes slower, you will hit the monkey later. All right, so that's the answer to that question. The other observation that we were focusing on is what happens inside an airplane in air turbulence. All right, so what's happening here is the passengers are getting slammed against the ceiling. So how's that possible? Given the fact that in all appearance that right at this point, if you're looking at it, looks like projectile motion, right? In projectile motion, airplane and the passengers inside should be moving at the same rate. So which means that if you're not wearing your seatbelt, you shouldn't be hitting the ceiling. All right, relative to the airplane, you should not be moving. Just like the person inside the elevator, falling elevator, you should not be moving relative to the elevator when the cable snaps. It's the same. You shouldn't be moving relative to the airplane when the airplane starts to fall if it's projectile motion, if the motion is under the influence of gravity. All right, so what's happening here is the motion is not under the influence of gravity. Our passengers are falling under the influence of gravity, but not the airplane. Airplane is being pushed down at a rate larger than the gravitational acceleration. As a result, the ceiling comes down and hits the people in the head. So from the perspective of people inside, it looks like the people are getting slammed against the ceiling. Let's build up to that question. All right, so which bullet lands first? The one which is dropped or the other one which is fired parallel to the ground from the same height? To answer that question, both of them will land at the same time. Both of them will land at the same time because projectile motion is the same as free fall. All right, gravity is going to have the same effect on a falling object. So the bullet dropped and the bullet fired from the same height, parallel to the ground, will land at the same time. So if it's a 4-second arc, and with an initial horizontal speed, 4-second arc with an initial speed whose horizontal component is 30 miles per hour, what's the horizontal speed of an object 1 second later? Horizontal speed is not going to change, right? So 1 second later, it's still going to be moving at 30. 2 seconds later, it's still going to be moving at 30 miles per hour. 3 seconds later, likewise. So the horizontal speed is not going to change. All right, so I'm going to just skip around just a little bit. So if that's the case, what's the value of the horizontal acceleration in projectile motion? If the horizontal speed doesn't change, the horizontal acceleration is going to be 0. So it's going to be 0, it's going to be constant. All right, so going back to the same question. So it's still a 4-second arc. The vertical component of the initial speed, this time it's going to be 20 meters per second. So, which means that it's going up against gravity. 1 second later, it's going to be 10. 2 seconds later, it's going to be 0. 3 seconds later, it's going to be 10, pointing in the downward direction. So, which means that the acceleration, vertical acceleration in projectile motion is going to be 10 meters per second squared. It's going to be constant. It's going to be 10. Horizontal acceleration is 0 and constant. Vertical acceleration is 10 and constant, which means that the projectile motion is predictable motion. All right.